Hello everyone, welcome to lecture 4 of week 8 of the course Power Network Analysis, in which we continue our discussion on Newton Raphson technique for solving power flow equations. And in today's discussion, we will specifically consider the application of Newton Raphson for solving power flow equations when voltage phasors of every bus are in rectangular coordinates. What I mean by rectangular coordinates is that if I have to indicate or write the voltage phasor at bus I, then it has a real part which is EI with an imaginary part Fi, where J is the complex operator -1. And analogously, these EI and Fi, they are nothing but magnitude of voltage with cos theta I. Theta I is the phase angle, and Fi, the imaginary part, is with respect to Vi sin theta I, where again the importance of reference or angle reference is important. So if phase angle theta I is being measured with respect to some reference, which is usually the slack bus or the angle reference bus or swing bus, then all these imaginary parts and real parts, they are also being measured with respect to this particular angle reference bus or slack bus. So we would assume our voltage phasors to be of this form and then see how Newton Raphson technique can be used to solve power flow equations in rectangular coordinates. In the previous lecture, we have at length discussed about application of Newton Raphson technique for power flow equations in polar coordinates, means voltages were having a voltage magnitude as well as a phase angle. And we have also seen the quadratic convergence or mathematical rigor behind proving quadratic convergence of Newton Raphson technique. So we will start this discussion with an example of understanding how Newton Raphson technique. So basically, the terminology is a little wrong here. This is actually one iteration of Newton Raphson method. Pardon me for using the same example from the Gauss-Seidel slides or Gauss-Seidel lectures. So the problem statement remains the same. We have a 3-bus network where bus 1 is the angle reference bus with voltage magnitude of 1 pu. Bus 2 is a PQ bus or a load bus, whereas bus 3 is a PV bus with voltage magnitude of 1.05, PG as 1 pu, and reactive generation should be within -1 and 1 pu. We will have to see how Newton Raphson technique works for one iteration of solving the corresponding voltage phasors in polar coordinates. That means the voltage magnitudes and the corresponding voltage phase angles. The line reactances, they are given in per unit. So basically we can find the corresponding Y bus. Please cross check that this Y bus is correct. And since we have 3 types of buses, so for every such bus we get to know what are the corresponding knowns and unknowns. Bus 1 is slack bus, so there is actually no unknown in terms of voltage states. For the slack bus, its magnitude is 1 pu. Angle can be chosen as 0 degrees or 0 radians for the sake of convenience. Bus 2 is a PQ bus, it's only a load bus, so basically -1.5 and -1.5, the values given over here are the respective real and reactive injections at these corresponding bus 2 PQ bus. Bus 3 is a PV bus, so its P is given, voltage magnitude is given. The unknowns are 3. The voltage phase angles of bus 2 and bus 3 and the voltage magnitude of bus 2. Voltage magnitudes of bus 1 and bus 3 are given or specified. If we have 3 unknowns, we choose the corresponding 3 equations, and prior information which is known to us are the voltage and phase angles of bus 1, voltage of bus 3. We have 3 unknowns, so we need 3 equations. Those 3 equations pertain to real power equations of all buses except the slack bus. So basically the real and reactive power equations exist for PQ buses, whereas we only have the PV. Bus 3 is that PV bus, so we have only P equation for bus 3, whereas for bus 2 we have both P and Q equations. We have 3 equations, 3 unknowns, the corresponding function forms of P2, P3 depending on the corresponding Y bus elements which are shown over here, and the values which are known above. Those function values have been given. Once we know these function values, we can correspondingly evaluate the corresponding derivatives for the initial choice of values that we choose. Injections at this initial solution, basically with voltage phase angles 0, you can easily cross check if angles are 0, the corresponding sign values would also be 0. So P2 and P3 for the initial values of theta 2 and theta 3 as 0 turn out to be perfectly 0, whereas for Q2 the cosine values, they turn out to be equal to 1, cosine of 0 is 1, voltage magnitude of V2 is chosen as flat start, which is 1. So essentially this term is 15, here we have minus 10, and here we have minus 5 into 1 into 1.05 and not 1 per unit. So basically this Q2 value is 15 minus 10 minus 5.25 which is minus 0.25, which is what is shown over here in terms of Q2 0. And similarly, we can also find injection at bus 3 because bus 3 is a PV bus. So we have to ensure that its generation is within the specified limit. So for the initial choice of solution, bus 3 remains as PV bus. We find the corresponding function forms, which is these numbers here. So 0 plus 1.5 is 1.5. 0 minus 1 is minus 1, minus 0.25 plus 1.5 is 1.25. So f of x at the initial value of x0 is this function order. And we can then find the corresponding Jacobian elements. The corresponding function forms were discussed in the previous slide. Once we get this Jacobian matrix form, always ensure or remember what sort of Jacobian we are looking at. We have two P equations, one Q equation, we have two voltage phase angles and one voltage unknown magnitude. So JP theta is a 2 cross 2 matrix, QV is 1 cross 1 matrix, Q theta is 2 cross 1 matrix, whereas JPV is 1 cross 2 matrix depending on the order of the knowns and unknowns. So we have this 3 cross 3 matrix as Jacobian matrix. We take its factorization, get the value of x1. So this is our initial x1, which is corresponding to theta 2 1, theta 3 1 and V2 1. 1 is the iteration number. We put in those values, get the next iterative values of all voltages, and this sort of a process continues till convergence. The process converges in only 4 iterations as compared to 19 recursions in Gauss-Seidel method in the previous lecture, which you can always go back and cross check, with the final solution remaining same as that obtained in the Gauss-Seidel method. So you can just have an estimate that number of recursion involved here is very high. The number of iterations involved in Newton Raphson is very small, but every iteration of Newton Raphson involves factorization of this Jacobian, furthermore evaluation of this Jacobian. And this value of j, it is likely going to change in every iteration because the corresponding values of V2 and theta 2, they are changing. So that's where the burdensome part is, and that's where the trade-off is. But still, for a smaller system, the number of iterations involved is much slower in Newton Raphson, and hence the convergence is faster and number of iterations involved is lesser. For rectangular coordinates, as I have already mentioned in the opening slide, that we are choosing voltage of bus I to be of the form EI plus J Fi, where J is equal to the complex operator. EI is the real part of Vi, Fi is the imaginary part of Vi, and if we use this notation and re-express our real and reactive power equations, these all turn out to be quadratic equations and not transcendental equations. And similarly, all our real and reactive power equations, bus injections at slack bus, real and reactive power generation, system loss, we have already seen these expressions, which we can evaluate once the power flow solution has been obtained. So with this as our premise of equations, the real and reactive power equations being quadratic functions, let's see how Newton Raphson technique can be used to find the unknowns, and those unknowns are real and imaginary parts of voltages at every such bus. So what we do is, we have the same convention that we choose bus 1 as our slack bus. We have our buses numbered from 1 to till capital N. and for sake of convenience we are choosing bus 1 as slack bus, which means it's the real part, the reference being the slack bus. So for slack bus, when you choose the phase angle as 0 degrees or radians, it is implicit that the corresponding real part, which is mod of v cos theta, would be simply equal to mod of v, because cos theta for 0 degrees is equal to 1. F on the other hand, mod of v sin theta. Theta being 0, sine would be 0. So irrespective of mod of v, f would always be 0. And that's the reason why for slack bus, we have E1 as the specified voltage magnitude, F as 0 degrees, choosing theta of slack bus as 0 degrees or radians with respect to potential or reference. For PV buses, voltage magnitude is specified. That means for every such PV bus, we know what is the specified value of voltage. But unfortunately, in Newton Raphson polar rectangular coordinate, voltage magnitude is not an explicit variable. The variables are all E's and F's. So how do we handle these E's and F's in terms of voltage magnitude? And remember, when voltage magnitude is specified, it implicitly means that for every PV bus, the sum of square of real and imaginary components will be equal to the voltage magnitude square. Why? Because E is V cos theta, F is V sin theta. So if we square them up and add them up, cos square theta plus sin square theta is equal to 1. So we have this unique equation. So essentially for every such PV bus, if it remains as a PV bus, this specified value is specified or fixed. So it has to be there, and E's and F's, they should ensure together that their square sum is equal to mod of V square. So how do we handle that in this? Because in rectangular coordinate for Newton Raphson, voltage magnitude is not an explicit variable. The getaway or get around for this is, okay, if the equation doesn't exist, let us include that equation and then we'll see what happens. And that is the reason why this equation is inherently present or written over here. In polar coordinates, the power flow equations that we saw, they were limited only to the first two equations. For Newton Raphson in rectangular coordinates, where voltage magnitudes are specified for PV bus, we also have to ensure that this third equation should come in so that PV bus remain as PV bus. So basically, we have three sets of equations for Newton Raphson in rectangular coordinate. The first set refers to real power equations for all buses except the slack bus. So basically, P is n-1 equations. We have the same Q equations as we saw in Newton Raphson for polar coordinates, whose dimension is ND or NPQ, the number of PQ buses in the network. And then we have certain voltage magnitude expressions which are pertaining only to PV buses. So essentially, this number is n-1 minus ND or NPQ. n-1 is number of buses except slack bus. If we subtract the number of PQ buses from there, then we have this as our number of voltage equations. The unknowns here are E's and F's. So let's also look at what are the unknowns. The unknowns will be all F's pertaining to all buses except the slack bus. Why except slack bus? For slack bus, it is already chosen as 0. So except slack bus, which means the number of unknowns in terms of imaginary components of V's would be n-1 in number, and E's again would be for all buses except slack bus. Even for PV buses, we would have E's. So this is also n-1 in number. Why? Because in Newton Raphson rectangular coordinate, voltage magnitude is not a variable. It is a known value. And E's and F's together, they have to ensure that they satisfy the voltage magnitude specification. So we have basically in rectangular coordinate, we have 2n-2 unknowns. And do we have same number of equations for these unknowns? Yes, if we add these three terms here, we have same n2n-2 equations also, from which we can find these corresponding unknowns. So this is what the unknown vector is. Initial choice again is equivalent to flat start in Gauss-Seidel method or Newton Raphson polar version. The set of equations here are a little different. So we have 6 submatrices. JPF pertaining to partial derivative of real power with respect to imaginary part of voltages, JPE pertaining to partial derivative of real power equations with respect to real part of voltages. And since P, Q and the voltage expressions, their forms are known in terms of quadratic expressions, we can easily find those derivatives. The convergence criteria remains the same. The corresponding dimensions of these 6 submatrices, they are all given over here, and I request all to please cross-check and verify these expressions with respect to the previous forms of P's and F's and the voltage expressions which are given over here. So basically, if I have to, the first 2 sets, they are pretty easier to handle, pretty simpler to form. How do I get the corresponding JVF matrix? So if I look at JVF matrix, it is essentially partial derivative of V equation with respect to imaginary component of F. Now, if we look at the voltage equation, this is true only for PV buses. If I have to express this function as, let's say, some m of x, or let's say some m of E and F, where the ith equation is EI square plus FI square minus V specified I square, and I want to find the derivative of the mth I equation with respect to the jth F. The jth F, or let's say the kth F maybe. K is some other bus number which is not same as bus I. Since Fk is not present here at all, it is only the imaginary component of that same bus which is present over here. So this derivative would always be 0, whereas for the mth I derivative with respect to Fi, where, or let me, if I say K, where K is equal to I, means K is same as I, so Fi is appearing here. This derivative is 2 times of Fi, which is coming in because of this quadratic form. And that's the reason why off diagonal terms, they are 0 for JVF, whereas diagonal terms, they are the non-zero terms. Same logic is applicable for the E partial derivative forms. The first 2 forms are pretty simple. The third form is exactly similar to the form that we discussed for F matrix here. The handling of Q limits, which is the last part, exactly remains the same. PV to PQ switching, PQ to PV switching will keep happening depending on whether the reactive power injection equation is satisfied for every such PV bus. So during PV to PQ switching, the corresponding voltage equation is not to be considered because the voltage magnitude which was defined for PV bus is no more fixed. It has violated its reactive power control. So voltage now becomes free. Reactive equation is now frozen. So reactive power injection equation with new reset values of Qg comes in. So voltage magnitude is free to change for PV to PQ switching. For PQ to PV switching for a specified PV bus, instead of reactive power injection equation, voltage equation would come in and voltage magnitude is now a fixed value. So essentially, compared to Newton Raphson in rectangular coordinates and polar coordinates, the dimension of Jacobian matrix in rectangular coordinates, it remains the same irrespective of PV to PQ switching or PQ to PV switching, which is 2n minus 2 cross 2n minus 2. The order of equations change, while the Jacobian dimension doesn't. Order of equations changing means the Jacobian elements also have to change, but then compared to polar version, the Jacobian dimension was also changing additionally compared to the, in addition to the number of equations being changing. So that's a big difference as compared to polar version in rectangular coordinate. Irrespective of bus switching, the Jacobian elements change, but the order doesn't change, or the dimension of J doesn't change. We have already talked about the quadratic convergence of Newton Raphson in the previous lecture. For a well-defined system, generally the Newton Raphson converges in very limited number of iterations. It has robust convergence and mostly gives the high voltage solution, wherein high voltage means the solutions or voltage magnitudes are close to 1 per unit and phase angles are in order of few plus minus 45, 60 degrees, so on for well-defined systems. For low voltage solution, the voltage magnitude itself would tend towards 0 no matter what the phase angle is. So Newton Raphson usually provides the high voltage solution, although it can provide low voltage solution depending on the initial choice. For poor systems or ill-conditioned systems wherein the load is very high or the distribution line R by X ratio is very high or the network structure is very radial, the corresponding Y bus becomes diagonally non-dominant, and that is a big link here. The Y bus becoming diagonally non-dominant, which would mean that the Jacobian also becomes diagonally non-dominant, and all these expressions that we have seen here, you wonder or see that the Jacobian elements, they are functions of Y bus elements. So if Y bus elements are diagonally non-dominant, Jacobian would also become diagonally non-dominant, and that is what creates ill conditioning, means the corresponding inverse of J is difficult to evaluate. Overall nutshell, Newton Raphson, although has quadratic convergence, is iterative in nature. Every such iteration involves factorization or evaluation and factorization of a large Jacobian matrix for a large power network, which can become computationally burdensome. And in this regard, several researchers have spent their entire lives on how to mitigate or reduce this challenge of computationally burdensome aspect of Newton Raphson technique. Since this is a very basic course on how power networks work, so I won't be able to discuss details of those research works, but I can always introduce what those topics or contents would look like. There is something known as the use of optimal multiplier, wherein researchers have successfully been able to demonstrate that with use of this optimal multiplier technique, Jacobian factorization can be avoided in every iteration. In fact, with the use of optimal multiplier under certain operating conditions for a power network, Jacobian needs to be factorized only once, that too at the beginning of Newton Raphson technique, and the same factorized Jacobian then can be used to solve Newton Raphson equation, be it in polar version or rectangular version. That is one idea. So when you are limiting the number of factorization of Jacobian, automatically Newton Raphson, since it is already faster, becomes furthermore faster and can still give us the same solution which actually Newton Raphson would have given with multiple factorizations of Jacobian involved. The other technique is known as sparsity technique, in which instead of storing or saving the entire sparse Jacobian matrix, because Jacobian, it is heavily dependent on the Y bus. Typically for large power networks, Y bus also is a sparse matrix. What is sparse? The meaning of sparse is most of the elements in a particular matrix, if they turn out to be 0 with very few limited terms being non-zero, we call that to be a sparse matrix. So larger the number of 0 elements in Y bus, larger would be the sparsity. And why would elements in Y bus be 0? It would refer that the corresponding element, let's say m comma n element in Y bus, if it is 0, which it would mean that bus m is not connected to bus n directly. That's how sparsity comes in. If a network is highly meshed with strong interconnections, Y bus would also become a non-sparse matrix. It is not possible always to have highly interconnected power network. Power network also has limited interconnections. So larger the or lesser the interconnection is, more the sparseness comes in the Y bus. More sparseness in Y bus means Jacobian also becomes more sparse. And sparsity technique, they enable storing or saving this Jacobian matrix with limited non-zero solutions or elements being stored only. The remaining 0 elements, they are not stored at all, and through use of proper reduction and inversion techniques, the stored sparse or non-zero dense matrix can be easily factorized. That is what sparsity techniques refer to. People who are highly interested or motivated to understand more about optimal multiplier or sparsity techniques, please give a search and you would be able to find corresponding references wherein you can go through these techniques. There are several textbooks which probably I will provide or I'll give reference to in the next lecture, and you can go through those details at length. The next lecture, we will spend time on another technique, which is a industry grade solution. In fact, it is a variant of Newton Raphson technique known as fast decoupled method, which came up somewhere around in 1980s, to be precise, I believe 1979 or 1981, I'll have to cross it, but it is somewhere around 1980s, where one PhD student along with his supervisor, the student is Alsack, the supervisor is Brian Stott. Alsack and Stott, they together came up with this technique or variant of Newton Raphson method, which is fast decoupled method, and there is no theoretical basis for this, but they were able to numerically prove that fast decoupled method is actually a better method than Newton Raphson, and the problem that they were trying to attack was, can number of Jacobian factorizations be limited in Newton Raphson? They were able to come up with this fast decoupled method, which showed that with one factorization of Jacobian, the same solution as in Newton Raphson can still be obtained with lot of time being saved. So we will talk about this interesting technique, which was thanks to Alsack and Stott, and then we will see how it works in the next lecture. Thank you.